What is up? Welcome back to another episode of How to Algebra. In this episode, we are looking at more complicated logarithm equations. So we're going to look at 4 examples that I think demonstrate the point of simplifying and solving equations, logarithms that is. So let's get it. Okay, solving more complicated log equations. The process is going to be fairly simple. We're going to move everything that has a log or all logs to one side of the equation, and then the non-logs, a constant or if there's multiple constants, to the other side. It's no different than solving any other equation that has x in it, right? You want your variable on one side, in this case the log, and then the non-variable or non-log to the other side of the equal sign. When it comes to the log side, we're going to compress the logs as much as we can down into a single log, and then change the equation from log form into exponential form. So step number 3 is probably the most crucial and in terms of solving the equation, right? Like this is a must for sure, because typically the variable is going to be trapped inside of the argument of the log, and we need to somehow get the variable out. And the only way to do that is by changing it to exponential form. And then once we do that, we can solve for x. Once we get what we believe is the answer, we always want to go back and plug that answer into the log to ensure that the argument is positive. Otherwise, if it's 0 or negative, then there isn't a solution. So let's get right into number 1. So there's 4 examples. Okay, number 1. Log base 5, 3 plus log base 5, and the argument is x minus 4 equals 2. The logs are on the same side. The constant is on the opposite side. So we notice that the logs are being added. So this means we have to multiply the arguments. So we want to multiply the arguments, meaning these two. So a single log, log base 5, and then the argument is going to be the product of the two arguments. So x minus 4 times 3 equals 2. So we've got it down to 1 log. Here we want to convert this. So converting, there's a very specific method that we use to follow. Okay, so typically a log is shaped this way, right? You have the log, the notation. You have the base, which is a lower index. Then you have something in parentheses, which we call the argument. And then it's typically equal to some value or something else. In this case, we're going to call it the power. And you'll see that when we convert it, why I call this the power. Because when we convert it, we have the base, which is raised to the power, and it's equal to whatever the argument is of the log. So we use this kind of schematic to rearrange, converting back and forth between logs and exponential form. So this is a very good and useful screen. All right. So with that being said, the base is 5, and the power is going to be 2, and the argument is going to be 3 times x minus 4. Okay. This is a one variable problem, which we should all know how to do at this point. 5 squared is 25. We distribute the 3. And we solve for x. Okay, so right now we've come to the conclusion that x is equal to 37 thirds. 37 over 3. That's nice. However, we always want to take our answer and plug it into the log to make sure that the argument is in fact greater than 0, right? It has to be positive. Can't be 0 or less. So let's keep in mind that 37 thirds goes into x minus 4. So checking our answer, 37 thirds minus 4. Okay, 37 thirds, without a calculator, it's about 12.3, repeating. And 12 minus 4 is 8, right? Which is positive. That's what, like the actual value is irrelevant, but the fact that it's positive is what is the most important. So because this is positive, the argument is positive, then this is definitely an answer. Okay. Number 2. So here, it's best to identify that log x is the log in question, right? That's the minus 1 is the constant. So there's a difference between what's on your screen now and if the parentheses were to the right of 1. With that being said, we're going to move all the logs to one side. I'm going to add log x minus 3 to both sides because I want to make it positive. And then add 1 to both sides. So there's addition. So we're going to multiply the arguments. And then we now convert. So when there's no index or base, it's understood that it's 10. So 10 raised to 1 equals whatever this argument is here. So 10 to the power of 1 is just 10. Okay, this is looking nice. We're going to distribute. And then I'm going to add 10 or subtract 10 from both sides. So on the left, we're going to get 0. And now we have a quadratic on the right. So solving a quadratic for x, this is just factoring. Right, two numbers that multiply to make negative 10 that add up to negative 3 are 5 and 2. More specifically, negative 5 and positive 2. Since this value the b value is negative. Since this is equal to 0, we can flip the signs, and we see that x is either going to be 5, positive 5, or negative 2. So 5 and negative 2. So we have to test back in the original five and negative 2. So if I plug in 5, log of 5, that's positive. Log of 5 minus 3, 2, which is also positive. So 5 is straight. If we put negative 2, however, immediately log of negative 2, that's not good. Negative numbers can't go into logs. It's not in the domain. So we know that negative 2 is not a solution. But x equals 5 is Gucci. All right. Number 3. Minus. So this is division, why we want to divide the arguments. So a rookie mistake is going to be this right here, right? This isn't dividing the arguments. This is dividing the logs, right? So we don't want to divide the logs. We want to divide the arguments. So this is what we want. And this is equal to negative 2. Okay, rewriting this thing again, log base 10 raised to the negative 2 power equals whatever's right here. So 10 to the negative 2 equals 3 minus 4x divided by 200. Again, one variable. The ISOR is for sure this negative 2. So that's going to push the 10 underneath 1 and square it. Right, so this is 1 over 100. Right-hand side, no change. And we just start clearing the fraction. Multiply both sides by 200. So 200 divided by 100, that's nice. It's 2, which is equal to 3 minus 4x. I'm going to add 4x minus 2. So 4x is equal to 1. X is equal to a fourth. So let's check it. Going back to the original, when you plug in 1/4, 4 times a fourth is 1. So 3 minus 1 is 2. Positive number, basically. So this is good. Okay, natural log. Natural log is even easier. It's just like a regular log or the other three. The only difference is the base is e. That's the only difference. Logs to one side. So ln of 7. Subtract ln of 7 from both sides. Left-hand side, we get natural log 4x minus 3 minus natural log of 7, and this is equal to 2. Subtraction, so this is division. divide the arguments. Okay, now that we have it down to just one log, we're going to convert it to exponential form. So it is base e. So e squared equals all this. So e squared, that's just a number, equals 4x minus 3 divided by 7. All right, solving for x, multiply both sides by 7. Adding 3 to both sides. Dividing both sides by 4. So x is equal to 7e squared plus 3, all divided by 4. You say, well, how am I supposed to check this? Well, I mean, you can, particularly without a calculator, well, you can always ballpark these numbers, right? Like, all we want to know is the argument positive? I don't care what the argument is. I just need to know that it's positive. So, or just non-zero, greater than 0. So we definitely have a number, e squared. E is about 2.7-ish. So when you square it, it's definitely going to be in the neighborhood of whatever 2 times 2 is, but less than 9, right? So bigger than 4, less than, so some number bigger than 4, but less than 9. So you could just say like 5-ish probably. And 7 times 5 is 36, 35. 35 plus 3, 38. 38 divided by 4, well, it's going to be slightly less than 9. So it's a positive number, slightly less than 9. So maybe 8. Well, if that's the case, right, 8 times 4 is going to be 32. 32 minus 3 is definitely positive. So it's safe to say that this figure will work. Okay, so hopefully this has helped someone out. If you are unclear on why it needs to be positive, because if you think of how the log function looks and the domain of the log, right? Any input, the x value, you can choose any x value you want. And you're guaranteed, as long as it's positive, that it will, at some point, right, it'll intercept the function. You can get an output for every positive x input, right? There is a vertical asymptote at x equals 0, meaning that the graph will get infinitely close to the vertical asymptote, but it'll never be 0, right? X can never be 0. So that means 0 can never go into the log function. And with that being said, since the graph never crosses the x-axis, all of the negative x values are also off the table, right? There's no negative x that could ever go into this because it's simply not in the domain. So this is why we check and make sure that the argument is in fact positive, because otherwise it's no solution. All right, so hopefully this helps someone out. And as always, subscribe, like, comment, and let me know what you guys think. Peace.